Hey class. Today I thought we would start by looking at the gamma function. It is considered a special function, and the term is kind of vague. To my understanding, the special functions are functions which you have to rely on wishful thinking to define. Now it's a little more formal than that. But the idea is that you can't represent it with polynomials. So the exponential function, which is an important function, is still representable via the power series expansion, via Taylor series. You can still represent it as a polynomial, and the same thing with sine and cosine and the other trig functions. Whereas this particular function, it's not zero anywhere, and so even in the complex sense, whenever you extend it to the complex case, it's not zero anywhere. So that really limits your ability to define it in terms of a product of its roots. So there is no polynomial representation. It's defined as an integral, and this is something that we can evaluate. We've shown that there are numerical approaches for evaluating these things. But what made it interesting whenever it was first studied is that it is considered to be the factorial function, the extension to the real numbers, to the values in between the integers, the positive integers. And then it has the additional value that it's defined on the entire complex plane for all input z, where except for the non-positive integer numbers, so 0, -1, -2, and so forth. And the reason is because there's a pole at each one of those integers. Let's take a look. So this is the definition. And this is the functional relationship that makes it the factorial. So you go from z to z minus 1 times z minus 1, or times gamma of z minus 1. So if you apply it again, then you get z minus 1 times z minus 2 times gamma of z minus 2, and so on and so forth. Whenever z is a positive integer. And so that's great, but if you look at this, it's not intuitive. And then it's also not intuitive whether or not this is the only possible generalization for the factorial function. So I won't demonstrate that it is, but at least not this time around. But it has the additional quality of it hits the factorial values for all of the integer values. So it's an extension to all of the numbers in between. But it has the additional property that it's strictly increasing. It behaves as you would expect. So for values between 3 and 4, it's strictly increasing entirely in that range, and it's increasing so fast that it actually outgrows the exponential function. It has what's called logarithmic concavity, where e to the x, if you take the log of that, right, the natural log, that's just x. Well, that's not concave, that's linear. And so the gamma function, the generalization of the factorial function, is actually outgrowing this, so that if you take the log of this, you're still getting something that looks like x squared, or something super linear whenever you take the log of it, which is incredible growth. It's an extremely fast growing function, and then it's just interesting in general, right? Okay, so we have an input variable of z, and we have a variable of integration of x. So what are we looking at here? Okay, so it's an improper integral. So we have something that's running off to infinity. So that's a reason for for concern as to whether or not it converges. But whenever you write it in this form, then we see that the requirement that the integral converges is really just the requirement that e to the x outgrows the polynomials, and it does it in something faster than 1 over x, right? So it's always more than a factor of x faster than all of those terms, and in fact does drive it to 0, and it does it with gusto. It does it with great haste. So regardless of what the polynomial is, the fact that e to the x is the exponential function, it's going to take it to 0. But the larger the input of z, so the numerator is increasing with z, but the denominator, it only increases, it's only variant as a result of the integral, not as a result of the input parameter. So it's a little easier to imagine what we're working with if we just study special cases. So, okay, why is this not defined at 0? So if the input is 0, then we have something that's, then we have the integral of 1 over x times e to the x dx evaluated from 0 to infinity. Well, our very first evaluation, and remember, if we think of this as a sampling function, right? So we're sampling these values, as we'll see whenever we try to numerically integrate this. Then our very first evaluation is going to explode off to infinity. Right? So we get 1 over 0 times 1. Yeah, okay, that's not a terribly helpful little utility there. And so it's a little easier to work with infinities whenever you're dealing with it over the domain of over the variable of integration. But whenever your function evaluates to infinity, it's undefined at that point. It's not exactly clear what is going on at that point. So in complex analysis, we refer to these as poles, and depending on the power of this 0, right? So if it's to the 1, to the 2, or to the 3, and so on and so forth, then we say that it has a pole of order, whatever that power is. So here it's to the first power, but obviously that can increase as we as we move further and further negative. So there's a pole of order 1 at the origin, so that causes problems. But we see that when that's not the case, for the input greater than 0, then we have something that's a little more manageable. So we can work with that. Okay. So what happens whenever we plug in 1? So we get x to the 0 in the numerator, so that's just 1. And then we get e to the x in the denominator. So it's the integral of 1 over e to the x dx. But this is also e to the minus x. And so the integral of that is just negative e to the minus x. And so whenever we evaluate 1 over, or negative 1 over e to the infinity, or as it approaches that, then that first part is 0, and then minus a negative of 1 over e to the 0 is minus negative 1, which is positive 1. And so it's, you can't quite see it. So as desired, it's 1, which is what we would expect for 0 factorial. So z minus 1 factorial. Okay, that's great. It agrees with what we have in combinatorics. So whenever you have n choose k, if k is equal to n, then the combinations, then so you have n minus k factorial, right? So that's n factorial over n factorial times 0 factorial. And we want that to equal 1. So if you are looking for combinations and you want to know how many combinations there are where you select every item that was available, well, there's just the one. It's where you've selected the entire set. Right, so the gamma function agrees with that. And then as it turns out, it agrees with it with the factorial function everywhere. So how do we get the functional relationship from this? Okay, well, that's done by integration by parts. So okay, so whenever we're taking the derivative of a product, we have the product rule. So so if we take the derivative of, with respect to the variable t, of two values which both depend on t, then it's the derivative of the first times the second plus the derivative of the second times the first. Okay, so now if we integrate that on both sides, then we end up with this. So if we have a product, then the integral of that product, we're just assuming that it's the derivative of something else, that it is differential. And if it holds that they are continuous functions, that we can make that assumption. And these are polynomials, so their integral is differentiable. All right, this is a polynomial and this is the exponential function. Then we can apply this rule. Okay, so we have this integral, and we want to use integration by parts. So we take the integral of the differential of one times the other, plus the integral of that one times the derivative of the other. So we're applying the product rule in order to integrate by parts. Okay, so then so we want to let u, in this case, equal the polynomial. And v equal our exponential. So in this case, z is considered a constant whenever we're integrating this. So the gamma function, for the purposes of evaluating this integral, the gamma function it's a functional. It's taking an input and it's generating a function. So it's not as helpful as something that takes an input variable and it spits out an answer. So it does, in a sense, but you got to work for it a little more in the gamma function. So it's more abstract than the functions you've dealt with to this point. But it's not impossible, and as I'll show you, it is possible to solve it programmatically. Now, there's going to be better algorithms available than what we're going to use, but I'll show you that the numerical methods that we were discussing earlier are still applicable to something as monstrously ugly as this integral. And I think it's actually it's a bit of a clever integral. I think the fact that it defines the factorial function, which I abhorred whenever I was in middle school, and I discovered that there was this function that was defined where you have to count down and multiply. That's not an actual function, but as it turns out, it is, and it's continuous. It's well defined over certain areas. Continuous for the positive real numbers. So anyway, okay, enough of that. Okay, so we have u and v. So now we need to compute du and dv. Okay, so right. So I've highlighted the fact that this is a constant. So z minus 1 is considered to be a constant in this. So even though it is a variable for our function, again, we take in that variable and it defines one of a family. It chooses one of a family of integrals, where the only thing we're doing is varying the degree, the power of this variable right here, of this variable of integration. So it's a polynomial times 1 over the exponential function, or a polynomial divided by the exponential function. And the base, the variable in the polynomial is the same as the variable in the exponential function. So so it's essentially choosing one from this class of functions. But once you make that choice, it's constant. So as far as the integral is concerned, z is not a variable. We're just setting the stage for the integral, and then the integral is going to work on the variable x. And we'll see that later. Okay. So now we can rewrite this in terms of our integration by parts. Okay, and okay, so the integral of u dv is going to be so it's going to be u times dv evaluated from 0 to infinity. Okay, so we see that as x goes to infinity, this first one is x to some constant power divided by e to the x as x goes to infinity, or negative e to the x. Okay, well that ratio, the limit of that is always going to be 0. So this one disappears at that upper limit, and then at the lower limit we have x evaluated at 0. So that's 0 over 1. Okay, well that disappears too. But we haven't done nothing, right? So we've decremented the power of the exponential here, or the power of the degree to which the polynomial is raised here. And we have this new constant, z minus 1, out front. So now this is a constant with respect to the integration, so we can move it out. And now we see that this is in the form, this is exactly gamma of z minus 1. So we've recreated that functional expression where we can essentially recursively define the gamma function in terms of whatever it was one place ago, one step ago. And when that's the integers, then this devolves into the factorial function because it has the initial condition gamma of 1 equals 1. Okay, so that's the gamma function. Let's take a look at, we have something that we know we can't convert into some polynomial, and We don't really have any way of writing it other than this integral expression. There may be other forms, but none of them are significantly easier to work with. But I've asserted already that if you can get it to this, you have this sampling function. Surely there's something that we can do. Okay, so let's take a look at how we would deal with such a monstrosity, and then we'll move on to the topic for the day. Okay. Okay, so we have that integral, and it ranges from 0 to infinity. Am I really going to insist that we take an infinite number of samples, or even 4 billion samples? No, not exactly. So just like any software development, we're just going to throw some spaghetti at the wall and see what sticks. We just move. Like, we're not exactly sure what we need to do to define it, but we know what it needs to look like. We have these test criteria that we can work with. We have these specs to get started with. And so we just start. And by starting, by putting it in motion, and then by seeing, once there is some effort performed, where it is that we're at, then we can kind of figure out what we need to change to actually finish off the problem. So we start just by defining a gamma function. So gamma of z is going to be equal to some function. It's defined as an integral, so we know that it's a sum. It has some value dx. So we know that we're going to need to work with that. I've already suggested that we should work with dx in terms of powers of 2, so let's do that. And then we know that we have this sampling function, the integrand. So let's define that separately before we actually loop. So whenever you think of a sum, you should think of a loop. So before we enter the loop, just so we know what we're dealing with, let's define our integrand separately. And so it was the variable x raised to the power z minus 1, and it was multiplied by the exponential function, or it was actually divided by the exponential function raised to the power of x, which is the same as multiplying by e to the minus x. Okay, and then that's the integrand. And then whenever we compute our area under the curve, we're just going to let it run for a while. So we need to evaluate it up to infinity. We don't know what that looks like. So let's evaluate it 1,000,000 times. Okay. So then we use an accumulator because we're essentially adding these rectangles under the curve. But we discussed that rectangles, the air disappears very slowly. So that round off air, the area that we couldn't quite compute accurately, and we know to have missed, disappears very slowly. But if we use one of the other methods, so if we use either Simpson's rule or the RK4 algorithm or the Trapezoid Rule, then we should be fine. So let's use the trapezoid rule because it's easy to understand. So it's the average of adjacent evaluations. So our value x is just I times our step, and then z is the same as the input, and then we evaluate it twice and we take the average. And then we return the sum. Okay, so it's the factorial function, so we know what it should look like. At 1, ideally this would be 1. We'll see. No, something has gone horribly wrong. Oh, forgot to normalize it by multiplying by dx. Ah. That's definitely wrong. Alright, let's take a look and see what I have errored. Okay, let's try moving dx into the integrand. And let's try taking fewer samples. Okay, so we've defined a function which is getting smaller as we go. Which definitely is backwards. Hold on. I don't expect this to make a difference, but this should actually be adjacent evaluations. Alright, same result. Okay, so the larger our value z, the greater our dismay. So why would that be? So the first value in our integrand is our value x. But it shouldn't actually be that's varying. Let me see. Okay, so this is a version that I wrote beforehand. And the difference here, and I guess this is a really important thing to factor in, is that in each of the examples that I've done so far, our step size was exactly the same as our number of iterations. So remember that we had two things going on. So we have this improper integral. So we can think of it as the limit as r goes to infinity of an integral ranging from 0 to r. Right? So we've written it from 0 to infinity, but it's from 0 to r, and then r goes to infinity. And then we have this step size, dx, which normally we would define that in terms of like our summations. We'd have the sum ranging from n equals 0 to k, and then our dx or dt would equal that input range divided by k. And then as k goes to infinity, dx goes to 0. But we don't typically have this improper integral. So in setting these to be the same, it appears as though I've introduced some error. So let's see if that's the case. If we go back to one that wasn't copied and inserted, and we modify it so that we're taking many more, a factor of 1,000 times more samples than our step size, does that solve the problem for us? And it appears it does. So that's something to keep in mind whenever you try to numerically approximate improper integrals. So it's not actually possible to to evaluate it all the way to infinity, except through means of analysis. So except by pen and paper, you can't actually do those improper integrals. So you have to take a look at what you're evaluating and determine a reasonable cutoff. So the factorial function explodes. You're not going to be able to represent all of the integers anyway, using a 64-bit float. It grows too fast. You can't even represent it in 64 bits when you start with 32-bit numbers. So you have to define some cutoff. What is infinity? And here we've defined infinity as 1,000,000 times 1 divided by 1,000. So we've defined infinity here essentially as 1,000, where x is 1,000. So we're evaluating this from 0 to 1,000, which explains at least some of this error. Some of it might also be the floating point representation. So that's 5 factorial, which is correct. That should be 120. So because the exponential function grows so fast in proportion to x to the, with 6 as the input, z minus 1 is 5. So x to the 5 is nothing compared to e to the x from 0 to 1,000. So it's not until x gets on the order of whatever we've defined infinity to be, right? So here we've defined it to be 1,000. Okay, I don't really know what I just did there. But yeah, so but we wouldn't be able to represent 1,000 factorial anyway. So that's a reasonable assumption there. But this is a perfect example of how you have to just make these decisions for what it is that's possible to represent. So there are more efficient ways to represent factorial. You could do it in a loop. You could do it some other way, something that doesn't require 1,000,000 evaluations, and then these additional power computations and so forth. But we were demonstrating that we can generalize the factorial function, that we can represent it numerically in just a few lines of code, and that methods of numerical integration are valid as well. Okay, so that's a pretty involved example to get started with. My goal for the day, and I'm not sure how far we'll actually be able to get on this, is to demonstrate the creation of an API. So I'm going to do this twice. I'm going to do it this week and let me check. Yeah, and then I'll do it again next week, and we'll use different technologies both times. And we'll try and keep it simple. I mean, we only have less than an hour. I think we have something like 45 minutes left, maybe 35 minutes. Okay, so we'll just do a brief high-level overview of it. Okay, so today we're going to use C#. So we can create an API pretty easily in C#. And we can do it from the command line once you have .NET Core installed, just by creating the directory and then saying .NET new web. And it'll create a project with a namespace that matches the directory name. So your web project will match that. And then we're going to use React for the front end. So once you've installed Node and once you've installed npm, then you can use the npm application interface to create a React application. And yeah, we'll introduce you to Typescript, which is the best way to work with JavaScript in my opinion, because it gives you typing. It gives you some hint as to what the variable is supposed to be. It's harder to get started because it's not exactly C-style syntax, and there's a bit of a learning curve. And so, but you're declaring essentially the data types that you're expecting. So there's the familiar ones from C#, and then you have to learn how to deal with or how to declare JavaScript objects. So you declare them as records, and then you have to come up with the keys and the data types that they represent in advance. And so it's a little bit more work. You have to get started on it, but it is that holy grail of what you're looking for in software management, which is that it's maintainable. So I had an instructor whenever I was an undergraduate that would tell us that Unix, which was the gold standard for server operating systems for decades, was developed in just a few years, and the total cost of the project to develop that original Unix operating system was I wish I'd looked this up now instead of just relying on memory and anecdote. But it was less than it was a finite number of millions of dollars. It was probably less than $10 million, maybe around $2 or $3 million to develop it originally. But the amount of money that's been spent maintaining it since then, and on not just maintaining the operating system, but on individuals to manage it and so forth, is in the hundreds of millions or billions of dollars now. And so for the life of any software project that gets off the ground, the cost of creating that project is going to be dwarfed by the cost of maintaining it. Now, there are exceptions to this rule. So if your company goes bankrupt before you actually sell any licenses to your product, or if you're running it as a service model before you get any clients, or even after you get clients but you're just not able to keep the lights on, then it's entirely possible that you spent more money creating it than maintaining it. But your goal is to get something that is adopted, and if that happens, then you most definitely want it to be something that's easily maintained. And as far as JavaScript goes, TypeScript goes a long way into helping that. It helps you understand what it is that you're working with. And the requirement that it insists, which is that you know the data types that you're working with, is a perfectly reasonable requirement if you're the one developing it. Because if you don't know, then who does? Who has these answers? Okay, so our C# API is created, and it creates some default stuff for us. So obj is going to be a directory that you will learn to ignore. There's probably some stuff that means something in there, but whenever you build something, you're going to build it to the bin directory, so you don't really need to worry about it. Properties, which include launch settings. You may use some of this stuff, like the port number and so forth. But yeah, you'll use these, but it's not strictly coding that's happening there, and you don't necessarily need to change these. Okay, so I'm not going to be able in half an hour to give you the full rundown of everything that goes into developing an API. So again, let's focus on the 2080 rule, and I'll give you the gist of what you can do. And we'll talk about it a little bit more next week when we do this again in a different language. And you'll see what's common between them, but the bigger picture in terms of how it is that you secure your site, or you create the secure areas of your site, I'm not actually going to touch on in this class. We'll talk a little bit about SSL later in the semester, but you'll still be left with a bit of work to do on your own. But for now, let's talk about what we can work with. If I get a chance to talk about Jwt Authorization, or if I get the time to do some homework on OAuth, then on Open Authentication, then we can look at that. Okay, so this is just going to be a very simple program, and in fact we should already be able to do hello world. So we don't have anything just yet, but we do have this one endpoint where if you go to the root of the website, you'll get hello world, and we have this software in Postman which we can use to test that out. So let's just build what we have and see if we can access it. So we'll publish our work, which will compile it. We want it in release mode, and we're going to publish it to bin out. And you'll see it creates bin and out up here. Perfect. And then we want to run it. And so .NET is the application, and we pass in the DLL, and it knows how to deal with it. So even though it's not an exe, it's a linked library, and the .NET command line interface knows what to do with it. Okay, so it's running. In theory, we can access it on this. So let's go to our API testing tool, and there's some terminology associated with APIs, and it's gotten more complex. So whenever I was first starting out, everything was either a GET or a POST. And so GET is where everything you need is in the URL line, and POST is if there's like form data or something that was submitted with it. So you have this extra payload. And then it was probably already in place, and it was just my ignorance at the time, but I think there is more of an emphasis lately on these other verbs for whenever you access these endpoints. And so whether it's put, which is should have looked it up. There's a distinction between put and post. Patch, which is essentially update. Delete, which you're going to use whenever you're actually deleting something. Never had to use copy. Head, I'm sure, has some purpose. I'll have to take a look at what these other ones are. But I have used get, post, put, patch, delete. And I want to say I've used head at some point, but I can't quite remember. But if you're unsure, then get whenever everything's in the URL, post whenever you have some data, and then delete whenever it's the equivalent of a delete command to the API. Okay, so let's see. We have our hello world. That's great. So let's modify it and make sure that we're actually getting what we expect. So we'll just add, change this. Add some exclamation marks. Okay, so now we have to recompile and then start it again. So we recompile, we'll publish it again. Well, no. Okay. And then we run it. Okay. I don't think I did anything catastrophic. Okay, great. Everything's working. Okay, so it's working, but what do we have here? What exactly have we created here? Okay, so we would really like this to be in an easier to maintain format as far as the API goes. I have it where it's saying, use endpoints, and then it passes in a function. This is a lambda expression. And then it evaluates, or we define a function, we pass that in to use endpoints. And then whenever the application starts up, it calls our function. This is another example of a callback method. And it says, okay, well, whenever the user goes to root, asynchronously execute this function. So pass in a context, and then this await is just a keyword that goes with the async. So basically it says you can execute this whenever it's fine with you, Mr. Operating System. There's no hurry. And so this is the actual method that gets called. And if it was synchronous, then this and this would get called. But these are essentially courtesy methods whenever you're interacting with the operating system that says, look, you don't have to finish this if you got something better to do, but you know better than me what you're doing. Whenever you get the chance, run this statement and execute it from here on out. And so it allows a little more freedom for the CLR for the framework to choose how many threads remain active and which threads process. So ideally, you're not spending a whole lot of time spawning up and killing threads. You have a thread pool for parallelized work that, like, let's say you have maybe 16 threads or 12 threads or however many cores you have on your computer times 2, and you have a pool of that size or maybe twice that size, but you don't want to create any more, and because you would have to spend overhead and memory creating that additional thread, and then overhead killing it and so forth, and keeping track of it. You really want your workforce, your predefined workforce, to take care of everything for you. And whenever you do something like this, then it says, okay, well, don't worry about insisting that my stuff get done. If you need that thread to handle a new incoming request, go ahead and deal with that, and then come back and handle my work. And so these courtesy modifiers, async and await, which says, yeah, you can do this asynchronously. That's what they're doing. And so whatever language you're working in, it's worth at least being familiar with that async await pattern. I think it exists in JavaScript, it exists in C#, and there's variations of it for Go and C++, and I'm quite certain Java would have it as well. Okay, so but this is terrible. Let's improve on this. Okay, so let's go and create some controllers. So something that does this, but that we can manage, so that we don't have this one class with this one enormous function and thousands of lines of code to handle incoming requests. I want to break it up, just like in all other areas of software development. I want to break it up just a little bit to help myself out. Okay, so we'll create a controllers folder. And the first thing that I would do is create a ping controller. So it's just like that hello world method that we just dealt with, but it's an endpoint that tells us whether or not what we're dealing with is actually working. Okay, so we create a namespace, and that's the programmatic equivalent of bookkeeping. It's the directory name. So we'll use well, we're not dealing with security just yet because we don't have some mechanism to verify authorization or authentication. So we won't deal with those security concerns just yet. But we'll add an attribute that declares that it's an API controller, so that whenever the runtime uses reflection to find all of the controllers, it can find it. So we're just tagging it essentially. And then a convention that has come into favor lately, so it's a design pattern you should be acquainted with, is declaring instead of everything living at the root level for your API, to stick it under API, so that you're distinguishing between those requests for the UI, the index.html file, and then requests for your API. And then also you'll, in more sophisticated setups, you'll have a reverse proxy, and the API request will actually go to different sets of servers than the ones handling the files. So you would have something like Cloudflare, or some content distribution service that's actually serving your index.html file, and then your requests would go to your servers, or whatever cloud array is handling them, or however you have it configured. But we're dealing with simple stuff right now, so we'll just note that is a pattern. So by doing this, we're no longer looking at localhost 5000/ping. Now we're going to look at /API/ping. Okay, so that's it. That's the whole controller. Index means that we don't want to have to define anything beyond the controller itself, and then we'll return that action. And we're just going to return a status code of 200. Okay, and if you're unfamiliar with HTTP status codes, it tells you anything in the 200 range essentially means that your request completed. Anything in the 300 range means that your resource was moved, so it's either a redirect or it was permanently moved. Anything in the 400 range means that whatever you're looking for wasn't found, and I think 500 range is errors, so server errors and so forth. Okay, so we just want to indicate that everything went fine. Okay, so now when we go to our startup file, we're not using endpoints in that manner. We actually want to indicate that we're using routing, which is good, and then the endpoints will be determined by just mapping the controllers. So look for anything that has API controller as an attribute, as a class attribute, or that inherits from controller base. I'm not exactly sure which method it uses, which approach it uses, I should say. But it's one of the two. So we declare that here, and then we compile again. And then we debug. And we haven't defined configure services, so let's see what was missing. So we have this additional method up here, which we use to okay, so if you're not familiar with inversion of control containers, or there's another name than service collections, but it's Ioc containers. So if you're not familiar with dependency injection, then it's a pattern that you should definitely read up on, and it is wonderful. So we're not going to get too into it again because we're limited by time. Maybe in a future class I'll find a way to include that. But there are these design patterns that I highly recommend you become familiar with, and this is more than a pattern. This is a solid design principle. But essentially, inversion of control containers or dependency injection suggests that you shouldn't be newing up your own classes, right? So you should never have to call var foo equals new ping controller. Right? You have this thing, this service collection, or this Ioc container, it already knows about ping controller, and then it used reflection and it looked up everything that ping controller requires in its constructor in order. So we didn't define one for that controller, but if we had, then it would look it up and would say, oh hey, it needs all of these services. I can pass those in, and I will create the new instance for you, and I will maintain it in memory as long as necessary. And when it's time, whenever we're no longer needed, I'll get rid of it. And so you tell it in this configure services method where to find each of those data types. So if it's an interface, you tell it where to find the class implementation that you want to use that satisfies that interface definition. And then when the time comes, it'll create that. And then it creates this registry of all of the stuff that your classes will eventually need. And when that happens, or when it's actually needed, it's able to provide them in the manner, with the correct lifetime, the correct scope, and then it manages it for you. So once you go through the headache of setting it up in one method, one time, then anywhere your application needs it and any time it needs it, it is automatically provided to it. So it's a layer of indirection. You're no longer directly asking for what you need, which is great in a small project, but the more the project varies, the the more headaches it can create. And so it's additional work up front, but it adds to the maintainability of the project. So it's something that's definitely worth exploring. So for now, we are just going to add what we actually need. So let me see. We need MVC, maybe. Let's try that. And it might also be that I'm missing a using directive. So let's see. I might have forgotten to add a package. No, I don't think so. Okay, so let's try adding ASP.NET Core MVC. So we build it again, and then we run it. And it's working this time. And we got a 200 OK. So we got a response. It worked. So the controller that we added worked. Let's do one more example, and then we're not going to get a chance really to work on the UI. So you got to see how the project was created. I'll make sure to leave more time next week whenever we do this with Angular, but that is React. I think it's a fantastic framework for developing UI stuff. But we'll jump into Angular, and you can see their affinity for design patterns there as well, in just how everything is declared. But let's define one more get method so we can be sure that what we've created is actually doing a thing. Okay, so let's create a foo function. So foo, and then this one actually returns some new object. Let's see. We should. Let's just return an int array. 1, 1, 2, 21. We'll call it fib. Okay. Okay, so the index meant that we didn't have to specify anything, but we're not accessing the index. Now we're accessing fib. Was a get. API controller. Okay, so it didn't find it. Let's see. Oh, okay. So let's tell it what the name of our method is, and we'll tell it what it's producing as well. So the response type is application JSON. So we're filling out the header information correctly, and we need to compile. And let's see. And we have our array. So it is possible to set something up in a fair amount of time and have it return data to the UI. I'm sorry that we didn't get a chance to play with the UI more, or at all. In this case, you just got to see it get created and then ignored. But my focus was really more on the API this time around. So we'll toy again with the idea of creating the API and the UI separately next week. On Tuesday, we will discuss another proof. Okay, so have a great weekend. Congratulations on finishing the second exam. There's just a few more weeks of this class left. We have 4, 6, 7 lectures left, and then the final exam. So, okay, sorry that I posted this one so late. I hope it doesn't trouble any of you too much. Again, have a great weekend, and I'll speak to you next Tuesday.